Everybody, we are in week 11 of this particular course. In this week, we will look at digital to analog conversion and analog to digital conversion. So, in today's class, we shall take up digital to analog conversion, and before that we shall have a quick recap of what we discussed in the previous week, then need of conversion between analog and digital, and two techniques for digital to analog conversion. So, that we shall see. Very quickly, what we saw in week 10 is how we use Mealy model and Moore model to design synchronous sequential logic circuit, and we had a comparison of these two different modeling techniques. So, in Moore model we had seen that input affects the internal state and output is generated from those states only. So, input does not directly go to the output logic generation. So, in Mealy model the internal states as well as input together act and generate the output of that particular circuit. So, for which we have got certain advantages and disadvantages of both. So, in Mealy model we can get the output a bit quicker, more number of don't care states in the Karnaugh map based minimization, and a little bit less hardware, and in Moore model any transients in the input circuit is not signal is not passed to the output directly. So, once the transient stabilize, then the clocking happens and then the output is generated from the internal states. So, these are certain things that we had seen, and we knew how to convert one model to another. So, we saw the techniques. So, accordingly we can employ them, and depending on our requirement we can use one or the other. Okay. So, you also saw algorithmic state machine chart based design techniques, which is a flow diagram based method. It is preferred for larger state machines because state transition diagram is found inadequate or very complex to read when the number of these variables, number of states, number of inputs increase. Okay. And also we saw that state reduction techniques, the usefulness of it, and how it can be used to minimize a given synchronous logic circuit, and by which we can get a more a simpler circuit. Okay. So, this is in brief what we discussed in the last week. Now, we go to a very important thing about this digital manipulation of signal. So, the most of the real life signal that we encounter are analog in nature. Analog means continuously varying with time. Okay. And we had already seen that this digital manipulation is of advantageous, and more about it you will study in some future courses, or parallelly you are studying in signals and systems or digital signal processing, right. So, what is important is that we should be in a position to convert analog data to digital, okay, analog signal to digital signal. So, for which we need to have a something called analog to digital converter. In brief, it is called, the abbreviation, it is called ADC. Okay, right. So, consider a sound signal, audio signal, right. So, you have captured it through a microphone, and then analog to digital converter is converting it to a digital stream, right, and then you are doing some manipulation over here. So, some frequencies are boosted, some frequencies are attenuated and all, and you are, it is good that to have a digital processing technique because of its advantages, right. And after that you want to play it in a speaker, right, where the speaker will continuously change its position and generate the sound wave, right. So, for that we need to generate a continuous signal, continuous time signal, right. So, you need a digital to analog converter over there, right. So, this is the kind of thing that we expect when we are trying to manipulate an analog signal in a digital platform, right. So, at two ends we will be having analog to digital, I mean in one end analog to digital converter and another end digital to analog converter. Okay. So, this is the interface circuit, right. So, in this week we shall look into them, right. So, we will begin with digital to analog conversion, this part. Okay. Later we shall take up ADC, because in ADC, within ADC somewhere a concept of DAC is already there, right. So, it is better that we start from DAC, right. Now, let us see how we can get a digital to analog conversion done. So, remember, for a digital to analog conversion, the input is digital, right, and corresponding analog signal is to be generated. So, input is digital means what? Input will be in the form of a binary digit. Say if it is a 4-bit, then 1010 or 0011 or so. If it is a 3-digit 011, 100, some such thing, and output should be a voltage which corresponds to that particular this input, digital input combination, digital signal. Okay. So, if it is a voltage, otherwise it could be a current depending on some continuous time manifestation of the input signal, an equivalent manifestation. Okay. So, let us look at one circuit which is based on weighted resistor, right. So, what you see here is a circuit where this is the circuit under consideration. So, this is your R0, R1, R2, right, and this is your the voltage at this node, right, and this RL load resistance is very, very large in comparison to the resistances that you have there in these different branches. Okay. And to begin with, let us not bother about this part, okay, 2 to the power 0, etc. Let us just consider these are three voltages V0, V1 and V2. Okay. So, this particular circuit, just like this, how will it operate? So, if we apply KCL at this particular node, right, since current is very large over here, I mean the resistance is very large over here. So, the current is very small. So, you can neglect that part, right. So, that is what we have mentioned here. So, V0 minus VA by R0 is the current through this, V1 minus VA by R1 is the current through this, and V2 minus VA by R2 is the current through this, right. So, from KCL this should be equal to 0. Is it fine? Now, if you take all these VA by R0, VA by R1, VA by R2 to one side and divide, then this is the equation that you get, right. And in this particular equation, if you consider that your R1 is R0 by 2, okay, R2 is R0 by 4. So, that is why it is called weighted resistor. Okay. So, resistor values are like this, right. So, it is R0 divided by some integer power of 2. So, this is what you get, R0 by 2, R0 by 4, and then when you cancel out R0, okay, then what you get here is 1 upon 7 V0 plus 2 Vn plus 4 V2. Is it fine? So, this V0 and this is 2 times the V1 and this is the 4 times V2. So, to indicate that we have mentioned this is 2 to the power 0, 2 to the power 1 is 2, 2 to the power 2 is 4, and you can think of extending it beyond that, right. So, the weight final, the VA value that you get, the weight of V0 in that is what? 1 upon 7, whatever the voltage is there, it is 1 upon 7. Weight of V1 is 2 upon 7, 2 divided by 7. Weight of V2 is 2 to the power 2, that is 4 by 7, okay. And if you sum it up, you will get 7. So, this is the individual weights. Is it clear? The basic circuit, right? Now, if you look at these voltages V0, V1, V2, either we put plus 7 volt or 0 volt, okay, because these are digital input, right, either it is high or low. So, we consider high for 7 volt, okay, and low for 0 volt, right. So, this is one such case 0 0 1, right. Then what will happen? V naught is 7 volt, right. This is your V naught, V1 and V2, right, and this is 0 0 0, the output will be 1 volt, right. And if it is 1 0 1, 1 0 1, so this was 0 0 1, this is 1 0 1, right. So, this is 7 volt, this is 0 volt, this is V2 is 0 and this is V2, V1 is 0, V2 is 7, so 4 into 7. So, what you get here? It is 5 volt, right. So, this is the way the output voltage depending on the input combination will be calculated. And if you have all the input combinations, digital input combination from 0 0 0 to 1 1 1, okay, you have at the input side, then the corresponding analog output will be 0 volt, 1 volt to 7 volt, isn't it? And the list, these LSB weight, the voltage that you can calculate, I mean, which is also the resolution of it. So, this is 0 volt and this is 1 volt. So, this is 1 volt is what you see as the voltage that it can move from one value to another. Is it clear? Right. Now, if you extend it to 4 bit, if you extend it to 4 bit, what happens? So, this is R naught, this is R naught by 2, this is R naught by 4, and you can imagine the next value will be in the weighted resistor based method, it is R naught by 8, right. And again, if you apply KCL, just if you go on doing that, now it will be, the value will be 1 upon 15 V naught plus 2 V1 plus 4 V2 plus 8 V3, right. So, this position as 2 to the power 0, 2 to the power 1, 2 to the power 2 and 2 to the power 3. These are the corresponding binary weights for the digital data that is coming, right. And the LSB weight, earlier it was 1 upon 7 for the 3 bit case, now 4 bit case it is 1 upon 15, that is whatever the V naught value, it will be multiplied by 1 upon 15, right. This is fine. So, we can extend it to a n bit case, and in that case the output voltage over here, analog output that you see for a particular combination of the digital input will be given by this one, right. So, this is V naught and this is the n part will be your this V n minus 1 for n bit, because it is starting from 0. So, 0 to n minus 1, right, and LSB weight will be 2 to the power n minus 1. Is it fine? So, this is the way we can convert a digital input coming as a bit stream to a corresponding analog voltage. Is it clear? Right? There will be more associated circuitry and all for practical use. So, that part we shall take up in next class. Okay. So, the first part is what we understand how we can convert through a weighted resistor based method. Now, there are certain limitations that you can visualize for this particular method, okay, for which we shall move to another method which is found more useful. So, first of all, this depends on the weights of the resistors. So, this is we require precision resistor. So, this is one requirement, and the second one is the MSB resistor. This one you can see its value is R naught by 8 and this is R naught. Okay. So, how much current is taken? So, this is 7 volt and this is 7 volt. So, this is 1 upon 8, right. So, the current is as many times lower, higher than this one, right. So, for MSB, if it is a 4 bit case, it is 8 times more. If it is 8 bit case, right. So, it will be 2 to the power 7, because it is n minus 1 to the power n minus 1. So, 128 times more current will be flowing through the MSB, okay, MSB resistor, right. So, the loading of it, the associated issues like heat generation and all is becoming more and more troublesome when the number of bits increase in this particular method. Okay, this is a simple method, but this is one limitation that we find. Okay. And today we are talking about larger number of bits used in DAC. So, in that case we need to look at an alternative circuit. So, for smaller number of bits it is fine. Okay. So, for the alternate circuit, what we have is called binary ladder. Okay. This is a very useful circuit. So, the binary ladder, first we see the structure and then we analyze the circuit and then we shall move ahead. Okay. So, what you see, this is also, you can see this is a 2R, then R, 2R, R, 2R, R. This is the way it has been arranged. Okay. So, there is no such thing like R naught by 2, R naught by 4, R naught by 8 and so on and so forth. I mean, becomes a bit difficult. So, it is all of particular type, either 2R or R, and it is terminating here with 2R. Okay. Is it fine? So, this side, the further one is V naught, then this is V1, V2, V3. Earlier we started from this side was V naught. Okay, you remember that? Okay. So, this is small differences. Now, how we analyze this circuit, for which we use what is called Thevenin's theorem, right. So, in Thevenin's theorem we calculate Thevenin's voltage and Thevenin's resistance, right. So, here for this particular circuit we consider there is a cut over here and then we see that the circuit is seen from this side to the right hand side, okay, from the left hand side to the right hand side. So, this particular block over here we are trying to find the Thevenin equivalent. Okay. So, for this V naught, okay. So, VTH will be V naught into this is 2R by 2R plus 2R, right. This is the resistance, this is the resistance, this is open circuit, this is cut here, right. We know the how Thevenin theorem works. Okay. So, this is V naught by 2, fine. And what is the Thevenin equivalent resistance? So, 2R and 2R in parallel. So, this is R. So, this particular block can be written in this manner with a equivalent circuit obtained from Thevenin equivalent. So, V naught by 2 and this is R. Is it fine? Okay. So, this you need to understand from the basics of electrical circuit where Thevenin's theorem was taught. Okay. Now, you look at this larger block, this particular block. Okay. So, you consider that all other voltages are not present, okay, they are just there. Later on we shall include them. So, this is V naught by 2 and this is R and R. If we consider a cut over here, right, then this R and R, right, 2R and this 2R in parallel. So, again a parallel voltage is this Thevenin voltage, Thevenin resistance is R, and now V naught by 2 and this is V naught by 2 into 2R by 2R plus 2R. So, it will become V naught by 4. Is it fine? So, this particular block now comes over here like this, right. So, again you consider a cut over here and you will find that this is going over here like this in this particular block, right. And finally, if you further move forward, so you will be having plus minus, this is your ground, okay, and this is your R, this is your V naught by 16 and this is your, is it fine? So, this is what you are going to get. So, the VA over here that is available to the outside world is V naught by 16 and the output resistance is R. Is it okay? So, the V naught at the output over here is coming as V naught by 16. Is it clear? Now, let us look at what happens to the situation when V1 is present and others are not present. Okay. So, this is this case. Okay. So, in this case this 2R and 2R are in parallel, right, and becomes R. So, this is R and R 2R and this is 2R, and if you take a cut over here, it is similar to what we had seen before, only the number of stages to the right hand side is now less, one less. Okay. So, here first it is becoming V1 by 2 and R, then V1 by 4 R, and finally it will be V1 by 8, and for this also the output resistance seen will be R. Is it okay? So, V1 contributes as V1 by 8 in the final thing, and this is V naught by 16, and if you extend for all the other voltage input and use principle of superposition, you have these output voltages V naught by 16, V1 by 8, V2 by 4, V3 by 2, and if you add them up, then it is 1 upon 16 V naught plus 2 V1 plus 4 V2 plus 8 V3, isn't it? So, we see that 2 to the power 0 comes over here, 2 to the power 1, 2 to the power 2 and 2 to the power 3, right. So, these are the corresponding binary weights, and corresponding analog output will be here this way, right. Earlier it was 2 to the power n minus 1, now it is 2 to the power n. So, this is for n is equal to 4, that is what we see over here. Okay. Now, we can extend it for n bit, right. So, if we extend it for n bit, then we have for these binary weights corresponding to MSB will be 1 by 2, second MSB 1 by 4, third MSB 1 by 8, and nth MSB or the LSB will be 1 upon 2 to the power n, right. And corresponding output voltages are B by 2, B by 4, etc., etc., and if you add them up, you get the analog output. Is it okay? And if we consider a 5-bit ladder, just for an example, and we consider 0 as 0 volt, the digital binary input that is there, and 1 is 10 volt, logic low is 0 volt, logic high is 10 volt, corresponding the binary equivalent 0 and 1. Okay. Then the LSB will be 10 by 2 to the power 5, so 0.3125 volt, right, and the full scale voltage, right, when all the bits are 1. So, this is 10 into 1 plus 2 plus 4 plus 8 plus 16, right, you are putting those values divided by 2 to the 5. So, it is 9.6875 volt, okay, it is not 10 volt, okay, it is 9.6875 volt. Okay. So, few interesting thing about this ladder based DAC, right. So, in this case output impedance is always R regardless of the number of bits, okay, and if you here we have seen that the termination was with that part we have not discussed. So, if it is terminated with 2R, okay, then looking into any branch means in the ladder from any node, right, the impedance is seen as 2R. So, that is what you can analyze and see, and each digital source, so this is R and the 2R, so it will see a impedance as 3R, okay. So, for the digital source, so R and 2R put together it is 3R, right. So, each one of them will be having equal loading, right, and if it is not 2R, almost equal loading, I mean not much of a difference, not like what we had seen in the case of weighted resistor based method, where it is the MSB was for a 8-bit case 128 times more current, the resistance was carrying 128 times more current, okay. So, these are certain advantages, and instead of this 9.6875, okay, if you terminate it with 2R instead of this very high resistance, or if you terminate it with 2R, then the output voltage will be 9.6875 2R plus R by R plus 2R, okay. So, this is 6.4583 volt, okay. So, this you note for the sake of your understanding, if instead of a very high resistance, okay, some other value is used for termination, then what will be the corresponding voltage, is it fine? And then the corresponding current will be in that case 3.33 milliampere for each one of them, but for another value. So, it will be close to that value, it is not varying too much from one digital input source to another, okay. This is a good point about this method, okay. So, with this we come to the conclusion of the first part of the DSC discussion. So, what we have seen is that for digital manipulation of analog signal, analog to digital conversion is needed, and to get back the processed digital signal, digitally processed signal, which is after processing is in digital form, and we want to get back it into analog form, then digital to analog conversion is needed, okay. And we had seen two methods. In weighted register based method, in-bit digital to analog converter DAC has LSB weight of 1 upon 2 to the power n minus 1, and for analyzing that such circuit, Kirchhoff's current law KCL is useful. Okay. And for DAC used DAC using precision registers, okay, the for this weighted register based DAC, the precision registers are required, and MSB register handles 2 to the power n minus 1 times more current than LSB register. Okay. This we have already seen. And binary ladder based DAC has got weight for the LSB as 1 upon 2 to the power n, and Thevenin theorem is useful to analyze such circuit, and it has a constant output impedance irrespective of number of bits, and it can have equal loading for each input, okay, each digital input, which is a useful feature. So, with this we conclude this particular lecture. Thank you.